share?
Sure. Thank you, Ellie. And thank you, everyone, for joining today. You can go to the next slide. We're here to establish yet another technology in our pathways to decarbonization. You might remember the goal for MIT was to develop pathways to eliminate direct campus greenhouse gas emissions by 2050. And so you can see from this timeline that since 1916, from the beginning of our campus, we've always had a central utilities plan. It's in the picture with a circle around it. And back then it was at the back of campus. Now it's really very much center to our campus. But the evolution of our district energy started with coal as a primary energy source. MIT then transitioned to fuel oil and then to natural gas and then finally to a cogeneration facility. And with each step, MIT has become less carbon intensive. You can go to the next slide, Ellie. We have a two-part strategy to getting to our ultimate goal of zero campus direct emissions. We're now enabling large-scale renewable energy projects, and we're reducing our carbon footprint across our campus through generation, distribution, and end-use buildings. We're developing the energy infrastructure to get us the rest of the way to zero carbon emissions by comprehensively powering, heating, and cooling our campus using electricity, provided that the grid gets green and having that reliance on that energy source. You can go to the next slide. So our central utility plant here on campus produces it delivers chilled water for our air conditioning system. It heats both with steam and hot water to our buildings, and we also produce electricity for our campus buildings. Next slide. And part of our decarbonization study, we really are looking at a large range of technologies to explore. So we're really taking time to evaluate the range of technologies for MIT's consideration in our pathways investigation. You can go to the next slide. So we're pleased to welcome today Stephen Durfee, who is the campus energy manager at Virginia Tech, along with David Trexler and Chris Vaughn from Burns and McDonnell. They're partnering and they will be sharing insights from Virginia Tech's ongoing geothermal planning process, which integrates both a central and decentralized thermal systems across different campus zones. This offers a valuable parallel to the types of infrastructure that MIT is working with. We are also welcomed today by Carrie Smith, who's the founder of Sound Geothermal Corp and the principal of Gray Edge Group, which brings extensive experience designing and implementing ambient loop systems. He'll present two case studies, a new decentralized installation at Colorado Mesa University in Colorado, and a retrofit of a four-pipe system at Weber State University, a scenario with strong relevance to MIT's existing building systems and decarbonization challenges. So we welcome everyone, and with that, I'll give it to the team from Virginia Tech. Thank you so much.
Thank you very much for the kind introduction, and I welcome everyone out today to this webinar, and we hope that you come away with some information that you're going to find valuable and helpful in understanding decarbonization. And so we'll get right into it.
All right, so I agree, David. Yep, we're hopeful that you all can pull away some useful information and maybe can apply it to your campuses, okay? So again, Steve Durfee, I'm a AD for Energy Management here at Virginia Tech. And we thought that before we got into the slide deck, we'd talk just a little bit about Virginia Tech to give you a little bit of understanding of who we are as an organization. As you can see here, you know, we're a public land grant institution. We're a fairly large student body. We kind of have an urban campus, but it's in a very rural area. Quite nice. 12 million square feet, pretty significant budget. And I think we're 500 or 600 million a year in research funding. So significant operation and quite a bit of district energy systems of all various ages on campus. And we just recently went through a utility master plan, which is kind of why we're here today, is because, well, David Traxler and myself and more from his team and my team worked together to develop particularly a thermal district energy system master plan. And existing on our campus, what we have is 5 different components within our energy and utilities group. So we have a facilities team of about 600 people, and our energy and utilities group is about 100 individuals, and broken up into these 5 different areas. And you can see we have a cogeneration plant where we have several different boilers. We used to have coal. We haven't burned any coal in 5 years, so that's fantastic. We have a 6.25 megawatt steam turbine and generator there. We have 2 chilled water plants. We just did a $40 million upgrade to connect 2 district chiller plants into one central loop and bring some more satellite chillers off line and tie buildings into this loop and move away from that business of satellite chillers and getting to more efficient central plant type operations. So you can see some of the bullets there. Virginia Tech Electric Service is also unique in its own way that we have one of only 2 university-owned electrical distribution companies in the country. Appalachian State would be the other one, so that's neat. We've got like 6,500 customers, and Virginia Tech is one of them, and the rest are pretty much town. Those in town. We have miles and miles of mechanical utilities underground, as you do at MIT as well. And then our Office of Energy Management is also in this energy and utilities group, and that's the office I mainly head up, where we pretty much focus mostly on a lot of demand side management, everything efficiency related. And our group also supports the broader energy and utilities team strategically on developments such as this, where we're looking forward. So the idea of our utilities master plan was obviously, hey, we have similar to you, like I said, an existing, cogeneration plant. We have, 80% of our square footage is served by district steam, right? So not the most efficient system from a thermal perspective. So we, again, partnered with Burns McDonnell to develop a strategic plan, if you will, a master plan, where we would look at moving away from maybe some of these gas-fired steam boilers, and we do have distributed boilers too. I'm sure MIT does as well. We have numerous buildings that are not on our steam distribution system, and they have either steam boiler in the building or even a high efficiency boiler maybe within the building. But the idea would be long term is to move away from this and move over to like a typical low temperature hot water sort of loop. Okay. Next slide. So with that, I'll turn it over to David, and David will start talking to you about what we really want to hear about, which is about geothermal systems and how they apply here, and the various sort of concepts and sort of a hybrid approach that Virginia Tech is taking to thermal utilities in the future. Go ahead, David.
Thank you, Stephen. So Virginia Tech is a little bit unique, where depending on where you are on campus, there's different things, different utility types. And the top part of campus is an older part, and it's called the academic district. It's almost entirely served by district systems, steam and chilled water. As you move further south, it's the residential and dining hall and athletic district. And there it's a mix. Some buildings still don't have air conditioning. Some buildings are on the central system. Some buildings aren't on the central system. So it's a bit of a hodgepodge. And then in the southern part, the buildings are more spaced out, and it's the science and veterinary district of campus. And here it's almost all building level equipment. Very few of these buildings are on any kind of central system. And so we looked at this 3 different ways. And we looked at a generation 4 system, which is when you have a central plant geothermal and you distribute hot and chilled water to buildings. Also, we looked at a distributed geothermal system, or called an ambient loop system often, or a Gen 5 system. And that's when you circulate geothermal water to the buildings, and each building has building level heat pumps to be able to heat and cool the building. And we also looked at heat recovery chiller only systems, and so to look to see how they would perform. So I'll start with an academic district of campus. This area, like I said before, has mostly central utilities to these buildings. The peak cooling load is 10,000 tons. The peak heating load is 11,500 tons. You don't normally refer to tons for heating, but this gives you same units to compare the magnitude of the heating and cooling loads. The geothermal bore field can provide about 3,300 tons, and we have two heat recovery chillers that are 1,500 tons each. So the plan for this part of campus is a new hot water distribution loop to be installed and to connect to the existing buildings that are heated by steam, and then providing supplemental heating and cooling by existing plants as needed, since the peak load is 10,000 tons or 11,500 tons, and we're only providing about 3,000 tons. But I think you'll be surprised at the modeling results from this. So even though our plant is only about 1/3 the size of our load, we provide almost all of the heating for the buildings throughout the course of the year. You can see the graph on the right, where you have the heat recovery chiller Geo in green, how the gas cost for that is not even showing up on the graph. It's less than $1,000 compared to $2.7 million, or what they were paying for in steam. So even though the system is much smaller, it covers the greatest majority of hours throughout the year and results in over $1 million a year in savings and operating costs, and over 10,000 tons per year, or metric tons, in scope 1 and 2 emissions reduction. If you're only looking at scope 1, it's almost completely gone. So we'll move to the next area of campus. It's the life science and veterinary district. Here, most of the buildings have a building level equipment in them. And so it made a lot of sense, and plus the buildings are spread further apart, to do an ambient loop network. The piping is much more affordable. It's one plastic pipe instead of four metal pipes with insulation. And so here we had about 5,600 tons of heating, 5,600 tons of cooling, 6,500 tons of heating. So we sized the bore field for the total load of 6,500 tons, and we had building installed chillers and boilers, or chillers and heat pumps in our analysis. And the results were that we completely eliminated the need for gas in this area of the district or the campus, reduced the operating costs by about $900,000 a year, almost half, and reduce the carbon emissions almost half over what is currently being used on this area of campus. Now, the final area I'm going to talk about is the athletic and student life district. This consists mainly of the stadiums, athletic facilities. There are some offices in this area campus and some lecture buildings. But there are a lot of student housing and dining facilities. So here, two 1,500-ton heat recovery chillers, similar to the other central plant. And here we had new hot water and chill water distribution. The chill water just need to connect into the existing distribution, and this would be all new hot water distribution, since there is no hot water distribution on campus right now. And the loads are 6,300 tons for cooling and 4,900 tons for heating. And this is the result of this one. Heat recovery chillers alone, they save a significant amount of scope 1 emissions, about 80%. But when you look at scope 1 and 2, there's a smaller savings. That's mainly because the grid in this area isn't as clean as other areas in the country. But still, it's a pretty significant impact in scope 1 emissions. Now, I went ahead and I ran a geothermal scenario, and at that point, we almost completely eliminate the gas usage in this area of campus. The cost goes down, but still not as significantly as the other areas of campus, and carbon emissions goes down again. One thing I also want to point out, and it's been the same in all these scenarios, and it's going to show you on this next slide, and is that the electricity usage jumps pretty considerably in any one of these because now you're using electricity for heating and cooling, and the efficiency on the heating uses more energy than the cooling side. So here's a comparison all. When I first did this analysis, I got to the student life and sports district, and I was curious, like, why or there aren't the same amount of savings in this area? And it helped me when I looked at them all side by side. So on the bottom of each one of these is an hourly heating and cooling graph for the different areas. Some life sciences districts, that there's a pretty high hot water load even in the winter. And a lot of that's because these buildings have a lot of dehumidification in them. And there are a lot of larger campus buildings. So even if they're not occupied, you usually keep them climate controlled. Well, in the student life and sports, there was much lower hot water needs in the summer for dehumidification in these buildings. So the simultaneous wasn't there. And the winter is fantastic. You can see the chilled water and hot water graphs overlaying significantly or overlap significantly. And that makes sense because you have sporting events in the winter. You're using the athletic facilities quite a bit. And the dining facilities are being used a lot too. So there's a lot of heat generation, and that could be used for the heating the dorms. But you don't have the simultaneous in the summer. And that was a big reason that you didn't have such significant savings. The conclusion is buildings with high simultaneous loads have high savings potential. And simultaneous means there's heating and cooling, or areas of campus where there's heating and cooling going on at the same time. Different types of plants can work together on a campus. You don't have to say, my campus must be all central plant, or my campus must be all ambient loop. Your campus can be what makes the most sense within different areas of your campus. When existing central plants are serving buildings, it's easier to provide a central plant because the buildings are already set up for a central plant. They already have chilled water, they already have steam to hot water converters normally, which can be switched over hopefully to hot water. So it's a much easier process. But when all the equipment is located in the buildings, like building level boilers and chillers, then ambient loop is going to make a lot more sense, and it's going to be less costly to install. And thank you very much.
Thank you, David. Next, we're going to welcome Carrie Smith, if you want to go ahead and share your screen.
Let me see. Give me a second here.
And if you have any questions, go ahead and drop them
Okay.
in the
Are we?
Yep. Yep.
We're sharing?
Yep. Great.
Okay. We're going to talk a little bit about just a quick refresher on ambient temperatures. By the way, thank you for inviting me to present. I'm honored to do that. Anyway, what we're going to talk about is a real quick recap of what a one pipe loop is and our district system and the basis for our ATL. By the way, we just finished the standard writing for ATL through IATMO, which is the UMC and UHHCC codes and everything else. So we now have a national standard for one pipe loops, and that should be published, we hope, sometime later this year. And okay, so we can do all kinds of things with the system. You know, A one pipe loop and look is generally a single pipe that circulates ambient temperature water. That's in our case, we do not use uh, uh, any glycol in these loops, so it's all ambient temperature water. So we tend to keep it between 45 degrees and 95 degrees, depending on the season. So we have two types. We have this hairpin loop, and then we have a local, a roundy round loop, if you will, that we use through the campus, and uh, the we enjoy that. And but basically, we also took it around and found out that what we can do is make sub loops that are individually pumped, and then they're connected to a master central loop, and so that we form micro districts, as we call them, and stuff. The micro districts are capable of sharing literally energy from anywhere on the installation campus as we go through that. This is a rough schematic of what we're doing. We're using the single pipe loop, and we're able to take load diversity from just about anything. And on this campus, through the buildings and stuff, the diversity's in the buildings. We have stages. We look at the diversity of the building first. We look, then we go to the central loop, look at the diversity in the central loop. Then we go to the ground source system. Uh, and so we kind of stack this thing, and then if that's insufficient all the way through, we would go to a conventional boiler chiller building. I'm sorry, boiler cooling tower system. And we have multiple times. This you guys call it Generation 5. We call it Generation 6 or Generation 4 and Generation 5. But anyway, what we did was this is the HVAC system, and then what we're starting to do is we're starting to integrate the electric grid with this whole thing versus and our first move in this is an IT map of where the traffic is on campus, so we can anticipate where the loads are going to be, and we can start to use the master control system or the global management system to shed load or whatever have you through the campus. And we can tell where the students are going. We can look at where we may need to divert energy to in the various micro districts we have. And again, the big issue is shaving peaks and time of day rates and trying to eliminate those or minimize them at best. The systems use diversity, system COP, is what we use to measure this. We've come up with a calculation for that. And it's not COP of the unit, it is the COP of the central loop, which is basically the amount of pumping that we need to move the amount of energy, inclusive of diversity and line losses. So we use, as you know, not usually this part load analysis. We look at what we really need for the system because we have a 50-90 rule that 50% of the load will handle 90% of the year. And in doing that and looking at that, we're able to maximize the use of this. And we'll go into Mesa State and Colorado Mesa University and Weber State here in a bit. This part load analysis, by the way, is called the Blue Angel rule in Europe. We build things and work for energy, and we found out that if we appropriately apply the affinity laws for the pumps and fans uh, in the system, that we're able to minimize the amount of energy we use. And then we're looking at the thermal storage of the ground. What happens here in these systems is the sink and source of the ground source system changes, and the ground source system becomes simply a battery. And what happens in that battery, when we can turn around and store our energy 24 hours a year or seasonally or whatever have you, is that we're able to divert energy. But what we're doing now is we're starting to look at the ground properties for specific heat storage, and quantify that storage. Uh, you know, The nice thing about a central loop and stuff is we can look at how they're joined and everything else. We can use all these different things. We look at solar PV, air source, ground source, chillers, wastewater heat exchangers, industrial waste, and so forth. We use ground heat exchanger, and since that loop now has changed to thermal storage, we need less loop in the ground if we more actively control and measure what we're using. And of course, we have water source heat exchangers. When we add the electric component to this and stuff, we start to integrate that into the system. We now become holistic in our view and use of the system. And then we also have conventional CHP, cooling towers, microgrid isolation, and so forth to look at that. The goals for this are to optimize energy savings and minimize water use. We find that out here in the West to be a real seller for this thing uh, uh, as we go, because we are literally saving millions and millions of gallons of water with cooling towers that we don't have to use except in peak times. Because typically a 500 ton cooling tower takes about somewhere between 500 and 700 horsepower to run and stuff. The pump in the loop field takes 7.5 to 10 horsepower and stuff. There's quite a difference in consumption. We want to recover the wasted energy with the distributed energy loop. We want to reduce the cooling tower water and reduce electric load. And then we want to shift load, store energy in the bore fluid, and shed energy at night with the towers so that we can take advantage of our lower wet bulb temperatures as we go through that. Colorado Mesa University is located in Grand Junction, Colorado. It's a beautiful spot in the world. It started out when we started this loop in 2007 and started working with this. And we had a campus of 3,500 students. And we had, about 600, 700 tons to work with and everything else. We currently have on the system close to 3,300 tons, and we've moved it through. And as you'll see here a little bit later, uh, we divided that and added to this campus. So this is a new build out example because we're able to turn around and take that campus from 3,500 students to 14,000 students today, 25,000 students by 2030. This is a rough graph from the control system about exactly what the system looks like. We've got about 3.5 miles of pipeline in through this. There are actually 5 districts, and the districts uh, uh, are up here in the upper right and stuff like that. We have the first district, and as you can see, it's kind of split up into the Maverick Center is another district, the dorms and the stuff are a separate district. But all of these are currently interconnected, and this is a city campus and a half square mile radius, and we've got about 3.5 miles of 18-inch pipeline in the system. The nice thing that this is we started to link the system to a global demand switch, and you punch this button and you get 10 different ways to start shedding load. So if we get a call from Excel Energy or CT Generation or whatever have you, instead of you're gonna in the middle of the summer says we'd like you to reduce load if you can, we'll give you a bonus for it, and usually the bonus is about $10,000 a shot. So, we start to turn off the outside air. We start to set back the thermostats, turn off the outside air, and progressively lower the consumption on campus. So that's pretty neat when you look at that. So, uh, as I say, that single button gives you a load shedding ability. This is a graph of our an industry graph. This is a van. It's old. I'm sorry I didn't have a chance to update this with the new information we got. But for example, when we had about 800,000 square feet attached to the campus, you can see those dots, which is electric demand somewhere between 3 and 4 megawatts. And as we go through and we expanded the campus up to 1,000,002 square feet, we added 50% more. You can see that it still pretty well stays in that same range because the geothermal, the load shedding, and the diversity we have. and it becomes very valuable. By the way, these outlayers you see are usually the kids coming back to campus, opening up a new building or something. So we have certain points that they're outlays that then reserve and go back to the normal trend. We look at evaporative water saved, and this was a calculation that was done when there were about 1,200,000 feet of square at the power plant. We're saving about 1.2 million gallons a year. We've avoided some considerable amount of power. By the way, the savings on this campus and stuff with the geothermal, because it is an old campus and a new campus, is roughly about $2.5 million a year. And you'll find out that is replicated in Weber State. And of course, we don't, on this particular campus with the connected systems, we haven't fired the boiler since about 2012, except for supplemental heating hot water and one or two downtimes when we've had to do repairs or bringing up a new central loop or micro district. And in those cases, if it's during the winter, we might have to fire a boiler. And last year was the first year we actually fired a boiler to maintain temperature in the central loop. And the reason for that is we put 5 new buildings on the campus over the summer, and we have to look at what is going to happen and model what is going to happen and then react to what actually happens. So we have these backups. So we have these 20-year-old boilers that are supplementing the campus. This is a quick graph of the carbon reduction across campus since 2007. With the expansion and everything else in the current do that. So we've significantly reduced our carbon footprint. And by the way, most of the carbon is the old buildings, which are still on boilers as we go through that. And we're taking this campus, and what's happening is over the next 5 years, we will be doubling the size of the campus. We'll be putting in a new micro district that will be hooked to the main with its own control system, own pumping and everything else like that. And as you can see, it's starting to get to the point where this half-mile square of campus is starting to compress. The white buildings are the buildings that exist. The colored buildings that are in purple and red are buildings that are currently being built. The yellow buildings and orange buildings are buildings that will be added. So they'll be adding another 1,200,000 square feet to 1,003,000 square feet and approximately 3,000 tons to the campus. Weber State University, on the other hand, which is located in Ogden, Utah, is a second thing. We came across what is similar to MIT. They have a 4-pipe system. It's underground piping and supply. So we turned around in 2012 and started to retrofit this campus and look and see what we could do to do it. We've currently finished retrofitting the north part of campus, and we have another roughly 60% of campus that we just now this year are taking our first bite out of that and connecting it to the geothermal system or ambient loop system. Now, the interesting thing about this is in this 4-pipe system, we didn't have room or didn't want to spend the money on excavation on this campus. So what we did is we tied the system into the new buildings and the systems that are, by the way, distributed heat pumps into the chilled water system. For the shoulder months of the year when the chilled water system isn't active, that is supplying that part of the campus and stuff like that, we just use that chilled water supply. And by the way, it is a parallel system because that was what is existing. But we use the ambient, we pump that and give us the ambient temperature water we need. In the special peak loads, we actually have the buildings tied to both sides of the chilled water supply and the chilled water load, and the system control decides where it's going to draw its best temperature water in that chilled water system, because we've got about a 12-degree differential across that where we do it. So if we part of these buildings might be in the morning in the heating load and stuff, we might pull from the chilled water return. When we start air conditioning, we might pull from the chilled water system. And really, this started out with WSU, Weber State University, looking to be carbon neutral by 2025. They went through extensive lighting changes and other ECMs, energy conservation measures to do it, but we had this big gap. We were never going to get there. And the geothermal system actually modeled out as we go through to get this campus to that 50% reduction by 2050. And that is happening, and that's what we're seeing in the campus. So anyway, just real quick, this was our first loop field we put on. This is a central plant system that we're using the central plant as the main conjunction point with, to tie in the first set of loop fields. And then other loop fields are tied to the building. And again, they're plumbed in such a way that they can serve either the central loop or the building itself, whichever way. So we continually put backup into these systems, whether it be through the geothermal system or the ability. And the first year we initiated this program, we took the broiler use down to 6% of normal when we did it through that winter and stuff. And again, that was on the north side of campus as we looked through that. So these are some EUI graphs that just basically want to show you what happened. This was a commuter campus and stuff. So our previous distribution of energy when we were doing single buildings in central Pan, you can see that in the middle of the day, what is happening is the EUI of the buildings is up. It's concentrated into that short period, which is also a peak demand period and stuff. Once we put it in the geothermal system, we went to the second graph, and this is what we're seeing right now. So we're seeing some rejected at night, which is the right and left sides of the graph. We've got a reduction through the central time of day through the active use of the campus. And again, this campus has about doubled since the time we started on the project. What do we have? You know, we think the greenhouse gas emissions have been reduced by 31% for the baseline year of 2012. We've even added through that at this point in time 370,000 square feet. Our electric consumption is down by 29% because the use of the affinity laws and our pumping speeds. Our natural gas consumption across the entire campus, just by adding the geothermal, is about 33%, and the energy costs are down by 40%. So I also wanted to just throw this in here and stuff to say we can do this in a city. This is a project we have in Seoul, Korea. It's a Latte Tower, which was the 7th largest building in the world, tallest building in the world. We take we have 1,100 vertical boreholes that are placed underneath the building. Geothermal condition takes about 8,000 tons. We get additional energy from a closed loop vertical system. We get both the black water and the potable water is used as source sinks. So that's pretty much what I've got in through that. So.
Thanks so much. Thanks to all our speakers. If you want to stop sharing screen, I'm going to invite Julie Newman, our Director of Sustainability, to jump here with questions and answers. If you have questions for the speakers, go ahead and drop them in the chat here.
Excellent. And we always end up with more questions than we can cover. So what we do is if you send your questions along, if we don't get to it, please know that those questions get kept internally because it informs our own thinking, and then we can actually redistribute it back to the speakers to seek some additional input. So let me start off with questions for both of you. There seems to be, and let me just say, you can abstain from answering this, but there definitely seems to be a deep interest in the cost per metric ton for any of your technologies. Is that, and let's recognize that it will be different in your grids and your regions than it would be as applied to MIT. So for those listening, we would be learning from it and just curious on how you're gauging that. Are those numbers that from any of the case studies that can be shared?
We do
Go
not.
ahead, Dave.
We don't have them for Virginia Tech.
Okay.
I can tell you about Colorado Mesa,
Sure.
and what we have of the geothermal loop. We put $20.2 million into the central loop, serving about 4,000 tons, 3,500 tons.
Okay.
So, and we retrofit the buildings, but I think that's a one-to-one exchange. The equipment in the building would have cost the same if it were conventional or geothermal. We've even gone through some metrics that turn around and with the tax advantages today, even rooftops, which is basically the cheapest system going right now, is more expensive than geothermal. So now this is the lowest cost system out there for our choices.
Great. All right, I want to start off with Virginia Tech. Could we start off with you guys? Because I know 20 minutes is a lot to cover everything that you're both sharing with us, and we really appreciate you kind of pulling back the curtain on your efforts. On the Virginia, and I don't know if this goes to David or Stephen, I have to say, but can you give us a review of your ambient loop system? That was part of where we brought you into the mix today, was that there seemed to be deep interest from folks joining us from our own teams in that. I think who saw you presented IDEA. That's part of what raised our awareness of your work. Can one of you just kind of walk us through that, the more technical side of your ambient loop systems and how they fit into your interventions?
Yes.
Right.
So the ambient loop system that we have
And feel free
is,
to share slides if you have some, because I recall you might have some more technical slides that you really like, David.
I do have some
Yeah, I
slides.
bet. Yeah. So feel
Yeah.
free to just share a couple of those to give that overview for us. Thank you.
Okay. I'll share them right now. So a couple slides on the ambient loop systems, and let me go in presenter mode. So in the ambient loop system, one of the key ingredients that's going to save money, which Carrie just referenced, is the piping system is so much more affordable than insulated steel pipes, which are traditionally used for hot and chilled water system. This is just from RS Means, which is a estimating handbook, and it doesn't include the trenching. But for 24 inches of uninsulated horizontal pipe, it's $177 a foot or $354 for 2 feet. For four 24-inch insulated steel pipes, it's $11,000 a foot. Well, it doesn't take long when you're $11,000 a foot versus, $200 to $400 a foot. Albeit it doesn't include the trenching, the traffic, and all the other things you have to go into. But there's a real significant cost savings there when you're putting in district piping network. And that's what we saw, where the buildings were much further apart. You had a lot more piping. It just made sense to go with the ambient loop network. One thing you have to be really aware of, though, when you go ambient loop, is you have to have utilities and space in the building. You need mechanical room space. You probably are going to need to upgrade your electrical service to your building, or at least do some significant electrical work. You're going to have longer campus conversion processes, which may not be such a bad thing. Like Colorado Mesa, just like Carrie said, has been doing this since 2007. So it helps if you're doing it over time with your capital budget and expenditures of your campus. It's a little bit more equipment to maintain. So there are some definite and huge advantages, though. The water in the pipes that are circulating are basically a gigantic storage system for your energy that you get for basically free. And your horizontal piping also is dissipating heat to the ground, which is an advantage. Where your insulated systems, you never really want to exchange any energy with the ground around you. With your ambient loop system, any ground exchange is bonus. So that's a real advantage of those. If you're looking at a central plant system, the expediency is the main advantage. You can retrofit an entire campus from one location, especially if you already have hot water network on your campus. You can reuse existing chilled water and hot water piping if it exists, and you have a much shorter construction schedule. The drawbacks, and Carrie referenced this also, is that it's just less efficient. You can never really turn off a central plant. It's always running in some way. And the pumping energy is going to be higher because you're circulating two fluids throughout campus instead of one. Your buried piping is more expensive. The energy shared on campus is a function of your central plant equipment. And what this means is basically your central plant equipment is designed to share a certain amount of energy. But with an ambient loop network, the water going by can share an infinite amount of energy. Every building can extract or reject energy as much as it wants, just as long as the loop is between 45 and 95-ish degrees or 85 degrees. So there's a little bit more limitation. It's more expensive to expand the system because the piping network is more expensive. And if you have to add additional plant equipment, that's expensive. And your board field locations tend to want to be closer to the plant. Where a distributed system, you can put bore fields anywhere in the loop network. It doesn't really matter how close they are to anything other than the loop. So hopefully this gives a little bit more detail on how we looked at the Generation 4 system, which is a central plant system, versus an ambient loop network.
Yeah, isn't the ambient loop a little less invasive to install, David, as well? Like with the horizontal boring you can do underneath pathways and hardscapes, you don't have to necessarily dig, right?
It's called directional drilling, where you can actually bore, underground, under roadways. You can bore distances and come back up, and then you can pull pipe through. We have a contractor there that can do this at Virginia Tech with pipe up to 30 inches in diameter. So that's not possible with your traditional piping network. I'm glad you brought that up, Stephen.
Right. Well, that was attractive to our team. So we really like that. A little less invasive, in some sensitive areas.
Excellent. Well, I'm going to go through some questions that were submitted to us ahead of time, and there's some coming through the chat. So we'll see what we can get through. What are some of the common misconceptions that you hear about regarding decentralized or centralized approaches? And is there anything that you shared with us today that had challenged your pre-existing beliefs about either, with respect to, like in hindsight, looking back on the projects that you both designed and managed, right? Because you're informing those of us who are looking ahead now and others. So again, just coming back, why don't we start off with you, Carrie, and then we'll go to the Virginia Tech team. So are there misconceptions that you had to navigate with both centralized and decentralized systems as you attempted to to determine the best intervention for your two institutions that you shared?
Always. I guess the only thing I can say about this thing, we've been doing this since 2002. And so, it's a process of learning. And what we really just basically, we keep looking for negatives and we haven't found any. It
Sorry,
really is.
for both centralized
Yeah,
and
well,
decentralized. Yeah.
no, in the ATLs and so forth. But our biggest problem is engineers that don't realize there's a different way to do things. The one pipe system was basically designed in 1958 by Bell and Gossett and stuff. So it's been around for a hell of a long time. And stuff, and we just used it for different ways. But as we use that, we're using more and more the distributed assets, and they don't recognize that we can have, just as David said, he can have his loop field anywhere there is part of the system. That diversity that you have. What happens in the micro districts is you get hot spots, cold spots. Then you turn around and look as you build out to how do we mitigate that with the program. So it's basically lack of knowledge and lack of willingness to do something different. you know, and that's the major push we've had. You know, we figured out how to handle steam buildings. We figured out how to, you know, and turn around and retrofit them. There's just mechanical things you do, and this is one of the things MIT has to look at. And you know, they're just not seeing it. So it's a matter of taking a 20-year holistic look at the whole thing and then coming back
Mhm.
and saying, oh, well, then we can afford that.
Mhm. All right, how about Virginia Tech?
I think for us, some of the challenges have been around like our operations team, be honest, like in change, right? Trying to work the hurdles there, and they're important players on our organization. So there was some misconceptions there about, you know, current design, you know, the effective, you know, I guess you could say reliability of, you know, new type technology and serviceability. We're in a rural area, so it's a little different here.
Mm.
We're in a rural area, so, you know, the support can be sometimes challenging. But, you know, in talking to peers, we found that, you know, it's there, it's available. It's just you gotta do some research, network a lot. But yeah, I'd say our operations team have had, I think, not I would say misconceptions about, you know, these type systems, but probably just I think it's pretty common. I'm sure that some of your organizations here have probably, you know, had similar concerns, but there are things that we've been able to work through education and a lot of networking and some, you know, peer evaluations, such. David, what do you think?
I agree. I think a lot of times central plant operators have been working on similar equipment for many years, and like all of us, things that are different are alarming by nature. And so that is a concern for them. Also, I think they get concerned about job security, that if they switch to a different type of system, maybe they won't have a job anymore. So those are a couple obstacles. And then there was always the funding obstacle. Like, where is the money going to come from to pay for this, and how destructive it's going to be to the campus? In some places, they lengthen out the construction because they don't want to tear the entire campus up at once. They don't want that to be a campus's a student's experience for all 4 years of their college.
That's a good point. Well, I think you just brought up a great segue to a question on operations and maintenance considerations. You know, how do they compare from your experiences, not even just at these three case studies, if you will, but just from your experiences designing central and decentralized systems? How do operation maintenance considerations compare across these two systems with respect to what you just alluded to, staffing, complexity, long-term reliability? Anything that you found from your experiences? And my understanding at Virginia Tech is that you actually have both kinds of systems there. Is that correct, Stephen?
We don't have them yet. They're still in the
Well,
planning
they're on
stage.
the way.
So,
They're on the way. Okay, yeah. They're in the
yeah.
design stage. Got it.
Yeah, we're still learning from others, you know, such as
Okay.
Kerry and, you know, our peers, right? It's kind of nice to be in this position where we can look and watch what's working, what's not working
Yep.
for others. We're not really reinventing the wheel.
Yeah,
So, yeah.
that's fair.
Yeah.
Carrie, anything to add there? And then we'll go on to there's some great questions around life cycle costs that people on this call are interested. Go ahead.
You know, we're nearing the 20-year life cycle on our first buildings. And the units are still running. The ambient temperature loop basically cuts maintenance because you're giving the heat pump fluid at a temperature it loves, and it's ideal for it. So, you know, and we've seen 40-year lifespans out of some of the stuff in Washington State. And I guess the second thing I say is the number of people in the maintenance staff. And I'm going to just say that at Colorado Mesa University, there's 2 people that handle all of the central loop stuff and pull in a contractor if pipe breaks or whatever have you. So that goes to show you that the maintenance is minimal. We've had one backhoe problem, that we turn around. We built the system like a water system where we have crossovers and so forth, so there's not a lot to do there. At Weber State, there's 5. Now that's to manage that, a paltry 3,500 tons.
We have so many more questions for you, which we'll get back to on, but there's one more question in the chat here around whether an existing chilled water loop and steam, it says with an existing chilled water loop and steam, but not a hot water loop, could an ambient loop approach efficiently provide all of the HVAC? And again, when you answer that question, tell us what kind of campus what size campus you're envisioning, like as it applies to Virginia Tech, Mesa, other.
Well, I think,
Go ahead, Steve.
Terry, didn't you do that at Weber State?
Yeah,
well,
that's
okay.
exactly what we did.
Mhm.
We had that problem where we had the big central plant, everything else. What do we do with it? I mean, we've decommissioned the boilers for that end of the plant, and we just, the maintenance, everything it's just simpler. And plus the UI of the building is just going way down, so
Yeah.
Right. I think
everybody's happy.
when you get into this smaller modular type equipment, it's less sophisticated, honestly, than the large, district, plant, central plant, heat pumps, right? They're quite a bit more sophisticated. So maintenance is a little easier, and the technicians may not need to be as well, shall we say, higher priced technicians or hourly rates and all that. And they might be easier to find those, how it is with the workforce. It's difficult nowadays to find enough qualified technical people to service these things.
Great. Well, listen, we're just about at time. I know that we've got questions just as we all want to continue to learn here. So thanks everybody for taking the time to join us today. And thanks to Stephen and David and Carrie for taking the time out to present and just be transparent with us as we all continue to learn about what's happening with decarbonization around the country. So